All right. Thank you, everyone, for coming. So I am an assistant professor of physics at Eckerd College, which is in St. Petersburg, Florida, and I've been there for a year. And I just gave a talk 2 sessions ago on the other side of this partition about how I do scientific code. Here, I'm going to talk about my pet project, the thing that took away my cycles from my PDL development, and now I spend most of my time on this, which is unfortunate. I love PDL, but this has been a lot of fun. So this project started because I had used inline C. I'd actually used inline PDL PP, which hooks onto inline C. And I felt like there were aspects of it that just didn't work for me. And the more I thought about it, the more I'm like, this works great, but it doesn't feel like I'm doing Perl. I had ended up writing, if I was smart, I would have looked it up. I had this one script once that was like 60 lines of Perl, 300 lines of PDL PP, and there was one PDL PP function call, and it had like 15 arguments because there was no way for me to do some basic looping and then do a little bit of C here and then do some other stuff and then do some C here. And then, so every time like, oh, I need this extra bit of functionality in that analysis, I had to then add another argument or 2 or 3 into this enormous function call, and then I had to go all the way to the bottom of the script and I had to implement it down there, and it was ridiculous. So there was something in the way I was doing that which clearly was not working. And so when I discovered the tiny C compiler, it's a really fast ANSI, whatever, C99 compiler. It just doesn't have complex types. But apart from that, it has, it supports C99. And so it also supports JIT compiling. Like, well, that's neat. If I can JIT compile, I know a little bit of access. I can then get a function pointer and I can call the function. And so I ended up creating a little thing called C tiny compiler, which let you produce a little string and you'd say, hey, compile this. And then you could even say, you could even produce a little header string. And some other module could ask for your header and use that and compile against it and then ask you to link in your function pointers. And so it was almost a way to get around this thing, this big beef that I had with inline C, which is how the hell do I define one function in module 1, another function in module 2, and get them to, or basically call one function, one C function from another module. Does anybody know? Is this possible? I think it might be. It would have been wise if I'd solved that problem. But instead, I wrote C blocks, which I think is a very, as it's worked out, I think it's a very Perlish way to bring C into your Perl code. It adds a JIT compiler to your Perl interpreter. So what do I mean by this? Here's the hello world. So what it does is you have to say use C blocks, and that adds some keywords. Unlike Damien, I'm not afraid of C. So I implemented my keywords in C. It's a lot of code. Anyway, yeah, you should never do that now that he's written with his crazy irregular expressions. So you have to do that. It'll give you the keywords. It'll give you the keyword C block. And what C block does is, you can see it right here. Well, maybe I should just run it. You can see what happens. Okay, so we see it says, hello, hello, so sad it's already Wednesday. So if we run this, it runs. Okay, that's rather, okay. But what it did was it actually compiled this into a little function. It inserted that function pointer into an op in the parse tree so that it did print hello, it then ran that op, and then it ran this print. So it's actually JIT compiling that code. It JIT compiles it at your script's compile time, so it only does it once. All right, so let's, did I have a note to self? Oh yeah, sure, let's do this really quick. If we use C block filter does a lot of neat stuff. We're just going to use it to give a quick demonstration. The C block filter, if it's not given anything to do for filtering, which I'll get to in a little bit, it just shows you the code it's about to compile. So when I have this code here that's in this printf, what it actually does it puts it right here and it wraps it in a void opfunc this thing, which we won't go too far into that. At any rate, it basically wraps it into a function which it compiles, and then it extracts that function pointer. So it literally produces a function that it then calls. All right, now let's take a look at one of the cool things you can do with this, which is that you can use everything from the Perl API. You may not have realized it, but we loaded the entirety of the Perl API when we run this script, and it's like that, right? It takes no time. So let's see what this is supposed to do. It says, hello, the Perl conference. And then we're going to get that message, and we're going to print it, and then we're going to change it. And then after that, we'll see what happens. So if we run it, the printf in the C block says what we expected it to say, and then we actually change the contents of that SV because it's just an SV, right? So we have access to that. But there's something very sneaky going on here, right? Because that's just a sigil thing. C doesn't know what sigils are, right? Okay, so if we actually, again, use this, we can see what's going on. Oh, what did I do? Filter, single. There we go. All right. You can see what it did was it actually identified this $ variable thing. It then ended up replacing that in place with this Perl scalar message and associating that Perl scalar message with the proper thing on the pad. So you can actually go right into your Perl variables and you have SVs in your C code. So you can do all kinds of stuff. And you have access to the full API. Now, let's see what else you can do. You can create a dual var. I mean, why not, right? So we'll just do this little trick where we upgrade our SV to be an SVT PVIV, and I had to read around on Perl guts to figure out how to do this. But anyway, so you do that. You then say, don't worry, the integer portion is fine. And then we can do string interpolation, and we get the string part, which was hello. And then we can do this part. Does that give, oh, you tried to add something to a string? No, it works just fine, because I set the numeric part. And I said it was fine. I have a dual var, right? I don't even have to use the dual var package or whatever. So you have complete control over your SVs in this case. You can also create, this is the least pretty part of this interface, which is that you can create a C sub. So a C sub is the keyword. It takes a function name that you want. It will then produce the proper XS wrapper for it. But when I say XS wrapper, I mean function like signature. You still have to do all of the stuff that X sub PP does for you. So you have to declare, hey, I'm going to use some XS args, and I'm going to be returning X, So this is not XS as we use it. This is literally the C, and you have to do everything by hand. But you then have a function that you've implemented in C, which can take a list, and it can print everything in that list. You have items, right? You have the stack pointer. So if we run this, it should. Well, let's see what it does. Oops. So it says, hello, PDL folk, because that was the first argument, and Chicago.pm, because I used to be an active member there, and DC Baltimore, because they're the wonderful people putting us on. So now we have a way of doing this. I'm not very happy with this. I'd like to make that better, but I haven't gotten there yet. So there are two more keywords that really make this what's cool. Because so far what I've said is nothing really any better than inline C, right? Except that it's using some crazy TCC thing, which is not your usual compiler. So, before I get to that. So before I said if you have a dollar thing in your C code, it will say, oh yes, you meant that to be the SV. Unless you specify a type. And if you specify a type, the package associated with that type, which in this case is defined in C blocks, types, and, or whatever, it has little Perl functions that return how to unpack and repack that. So, wow, I'm already halfway in. Okay, so in that case, here, this is going to be an int, a C int. And so outside of the C block, I think of it as a number because I assigned a number to it. Inside the C block, I think of it as a number because it's already unwrapped it for me. So if I run this, then it'll print yay many times because I told it to do that, and I can add more if I wanted. And it automatically does this for me. All right, now let's keep going. This is neat because you have an int array, which is like 1/50th the power of a PDL array, but you still got it. And, okay, so you can do that. It basically treats your SV buffer as if it were an array, and it handles all the casting for you. But let's keep going. Types are not constraints, so if I say I have an unsigned integer called foo and I assigned hello to it, Perl has no problem with this. And then I can run it and I get argument hello isn't numeric. The problem actually occurs in that unwrapping code where I try to get an integer, an unsigned integer value from the SV. That's where the warning occurs. So this doesn't do type constraints. It's just kind of a hint for C blocks. Okay, now let's talk about the real, like, the thing you should care about, which is sharing functions. This is a lexically scoped visible function and some integers. So this is a random number generator that I stole from this book, and he said you should always change the numbers you put in here, and I copied them verbatim. And so now I create this Perl variable. I say it's an unsigned integer so that when I assign to it, it properly unpacks and repacks and everything. I call this function, which basically updates the state that's maintained by these 4 variables, and it returns whatever that is, and then I can print it, right? And so if I run this repeatedly, I'll always get the same thing. Okay, that's not terribly useful, except I could loop over this and produce a whole bunch of randomly generated numbers using this algorithm. So you're like, okay, well that's kind of neat because now I have a function. You may not have realized the C block could not hold function declarations. It could only have code that is going to be run immediately. I think actually TCC won't croak, but that doesn't mean you should use it because I don't know how you would get access to them. In this case, there's something very powerful going on, which is why it took me 3 years, which is that after you've compiled this, it asks TCC for the symbol table. That was fun to teach TCC how to do. It then stores that in a lexical in the hints hash. Don't worry about it. It's cool. And then when you get to the C block down here, the C block says, hey, what is in my, like, what are the symbol tables I should have access to? Do you happen to know of this function called kiss? And they say, oh yes, here it is. Here's the function pointer. And then I can call it. So that's how that works. So that in and of itself is pretty cool because you can declare your function. It's actually kind of annoying that you have to have 2 keywords, one to declare your functions and one to declare your code. But that's the only way I could get it to work because of the way C works. This is the magic. A C share block adds an additional little bit. It stores its little function point, or it stores the symbol table pointer in a different, well, 2 places. First of all, it's lexically available, so I have access to this function within this module if I needed to use it, which is why I can assign these values of x in a C block. But then, when I say use my random number generator, this C block has access to the code defined in here. And the export happens, it's just kind of a built-in import method for this. Okay, so if I run this, you'll notice, by the way, we now have totally random initializations for these, so we should get different random numbers when we actually run this guy. So if I run it, I get different random numbers. Oh yes, I wanted to demonstrate lexical scoping because the actual availability of these functions or of anything that was defined in a given symbol table is lexically scoped. So if I have this, that's just because the hints hash works this way, right? So I've now embedded my use statement within a block. And now if I try to run this, it says I have a compile time error. And if I had line numbering, you can see that this is line 14. It says kiss is undeclared. So I can control the visibility of functions or globals lexically. I create a new scope. I say use this, use this, use this. And then when I get out of that, if I have something else that's defining functions with those same names, they're not going to collide. Okay, how much does this cost? I have 4 different timings going on: use strict and use warnings, use strict warnings and C blocks, use strict warnings, C blocks, and types, and then I finally actually create something and modify it. And we can see roughly how much this costs. It's all pretty quick, but there's usually about a factor of 10 difference between this and this. Between actually compiling a little block and the execution, I'm sure, is quick, but the compilation stage does cost you a little bit, right? Because it's JIT compiling it. And so it's still quick, though. So if your actual operation is a lengthy operation, this is pretty short compared to that. Okay, now, I also, so in my Perl Advent thing for C blocks last December, I also tried to write a really wickedly clever C implementation of something that was going to like rip through a file and pull out information because I knew Perl was good at that. Okay, well let's see how, if we use Perl at its strength and then I tried to do some really clever C, what can I do? And my C code was like 20% slower. And it was like 10 times longer, right? And so obviously if you're doing I/O, if you're doing what Perl is good at, use Perl. This will speed up the stuff that C is good at speeding up. And of course, that's the point. That's why I wrote this, so that you can basically have a little block of C code that does what you needed to do, because this is the part that needs to be fast that C can do well. Okay, good. Do you have any idea how much time I have left? 4 minutes. Okay, so we'll see if I can get through some of these other things that are available. The thing I'm working on right now, I'll just jump right to it, is a simple object system that injects methods into your Perl class that you can call from Perl land, and the same vtable exists in C, so you can call them. And if you have a derived class that overrides a method with Perl, the C code will properly launch the Perl. So you can just call it, and it'll just work. And it worked last night until that's still it's almost where I want it to be because I want to get roles working. They're not 100% what you think of when you think of roles, but they're really close. Okay, so let's quickly go through some of these things that are also really helpful. You can transform code using source filters. They're source filters, but they're not. Yeah, okay, well they are that bad, but they're really helpful. You can actually have not genuine, but you can do pointers that are really helpful. I'll just run through them quickly. You can see them. A source filter you can say set up a C blocks filter, and you can pass it a string that begins with an ampersand, so it knows to look for this function name. You can't pass it a subref due to the way that everything is lexically scoped using hints hashes, and you can't put a subref in the hints hash. So you have to give it the name, and then it will call this, and it will apply it to the code that it gets. So then it will replace this loop with while one. Okay, that's kind of cute, right? But this is not the most useful case, but you can imagine that there could be situations where you want to craft some C code, but it's laborious to write or it's tedious to write, and you could just somehow do some sort of a declarative thing. It's up to you to write the processing, but all right, it's possible. This shows you actually what's going on. We started with this. We ran it through the filter because it said printing, doing it, and it replaced loop with while. Okay, good. Then another thing you could do is you can basically build up, you can do what are called interpolation blocks. So if in your C block you have a $ curly, this is going to be Perl code that returns a string to be injected. That means you can build up a whole bunch of C code. I'll just leave it at that. This one does pointers correctly. Turns out that's trickier than you might think. If you want to take the address of a pointer and store it in a pointer to a pointer. This one ports excess object magic to C blocks so that if you want to attach a pointer to a scalar, you can do it in a way that can't be attacked from Perl land. But it provides all the unpacking. So if you use that type, then you basically, in your C code, it's already been unpacked for you, and you just have that C object instead. What was I going to do about this? Oh yeah, so this gives you an example of that unpacking. So this was the module, this is the script. You can even work with that hash ref, and you can assign to it, and it still doesn't screw things up, because you're not able to modify that. All right. Finally, because all of this, TCC is a single-threaded thing, it uses lots of globals, but because your compilation of your Perl script is usually run in a single thread, usually, therefore, C blocks almost always works. It compiles, so here's just a straight-up Perl multi-threaded thing, right? And so I can run this, and it immediately says back in Perl because it immediately got there, and then it waits for all the threads. If I replace that print with a C block that does the same thing because we're boring, runs fine. because it did the compilation in a single thread, so it's not screwing up TCC. So this is my next thing. In the future, I mean, I'm done talking, but this is where I'd like to go, is to have an object system that works equally well in Perl and in C, so you can use wherever you need to be, you can do it. So that's all. Thank you very much.